Hi everyone, this is the setup video for the RC circuits lab. So an RC circuit just means that we have a circuit with R, resistance, and C, capacitance or capacitor. So we have a resistor and a capacitor. So that's our essential basic circuit here. So a capacitor is a device that will store electric charge. Okay, so we can actually, what we'll do in this lab is we'll use an ILM device to store up some charge into the capacitor, and the source of the energy, those charges, will be from the batteries inside the ILM device. Okay, and so what we'll do is we'll charge up this resistor and we'll discharge it. First, we'll do so through an LED. And then we'll discharge it through just a resistor, and we'll analyze that graphically and see, learn some things about capacitance. Okay, so first we'll start off by setting up our circuit. So of course we'll use our breadboard again. We will use a 10,000 ohm resistor. Okay, so the one we've been using. Okay, and I'm going to set that up. I have it in, looks like in the picture, I have it in B1 and B8. So I'll try to keep it like in the pictures in the lab manual. Okay, and then the capacitors are, we're going to use the ones that are in the MPN starts with RK1E560M. Okay, so there's two of them in your pack there, and this is the 56 microfarad capacitor, and you can actually see it says 56 microfarads written right on there. Okay, now recall that when we use resistors, it didn't matter which way we plugged it in, right? So I could plug the resistor in this way, I could flip it around the other way, and it would work the same way. With some capacitors though, it does matter how you orient them. So if you'll notice, your capacitors have, one end is longer, one of these, we call these leads, is longer than the other, okay? And so the way these work is that the longer one is essentially positive and the shorter one is negative. So when we plug it in the circuit, we're going to want the positive end to be facing towards the positive end of our circuit. So remember that the way we power our circuit, we'll use again this time the 3.3 volt port. Okay, and that will provide us with the positive end of our power. So if I plug that in to start the circuit here, if I plug it in to row 1, okay, the positive is going through this resistor, and if we put the capacitor in series, then I'll want the long end to go in row 8. Okay, and that will allow it to be facing toward the positive end of our power supply, the 3.3 volt port. Okay, and then it looks like I have in the picture, it's plugged into row 13, the negative end. Okay, and you could just bend those leads as you need to get it in there. And so then row 13, that's the negative side of the capacitor, is plugged into there. And so I'll plug my ground port. I'll use my black wire, like in the picture, and I'll connect that to the ground, one of the ground ports, any which one. Okay, now we have a full circuit, right? Power, current's leaving, going through the resistor, through the capacitor, back in, and forming that single pathway for the current to flow through. All right, and then once we turn on the ILM device, okay, once you turn it on, you see that lights start going. And if your software says connected, then it's already getting power. Okay, this capacitor is already charging up. So you don't even have to start any of the sensors in order to get the capacitor to charge up. And so it'll charge, so it'll just take maybe a few seconds to fully charge, okay? And so if we want to discharge it, like in part 1 of the lab manual, we want to discharge it through an LED. So we used the red LED before, and you can look at that and remember or observe now that there's also a longer and a shorter lead on here. So similar to the capacitor, there's a positive end and a negative end to your LED. Okay, and so we'll connect the positive end, the longer LED, toward the positive side of the capacitor. So I'll plug the positive there into row 8. Okay, and then, okay, so this is figure 2 now. And then I'll put the negative side. Okay, and I'll just put a row 8 on the other side of the divider so it's separated. Okay, and then I'm going to plug my green wire into row 8 there next to the LED, and then that way we'll be able to use the green wire. For me, I'm going to touch it to the negative end of the capacitor. We'll be able to see the LED discharge. So to prove that it's actually coming from the capacitor, we can unplug, disconnect our power source. Okay, and then if we touch that just to the negative lead, you'll see it very quickly. Okay, it's discharged very quickly, just a blink. Okay, now it's all of its charged is used up. So once you get that to blink like that, you know you've got your circuit, your RC circuit set up properly. Okay, and then we can move on to part 2. Okay, so for part 2, we'll just take out the green wire and the LED. We only use that just to make sure our circuit was hooked up right. Okay, but we'll still have our RC circuit here. And like we did in the Ohm's Law lab, we tried to find out what was the true resistance of our resistor, because these parts are cheap unless you're doing a very precise application, and you're just testing simple things. Usually you have cheap materials, and so that's the case of these materials. So we're going to find out in this lab what is the true capacitance of the 56 microfarad capacitor. Okay, and so when we say capacitance, right, remember that a resistor has resistance. Okay, a capacitor we say is capacitance. So it's the capacity that the capacitor has to store electric charge. Okay, and so what I'm going to do is, like in figure 3, you'll see now I'm going to connect my green wire to the positive end of the capacitor, right, row 8 there. And I'm going to connect that to the analog 7, the A7 sensor on the IOLab device. Okay, and remember that when we connect the analog 7 sensor, reads the voltage drop between wherever you connect the A7 port to and between that and the ground. So the way we have it set up here, we'll measure the voltage drop across the capacitor. Okay, and so what we'll do is we can go ahead and plug our 3.3 volt port back in to get that capacitor charging. And then to discharge it, I'm going to connect my white wire to the negative end of my capacitor. Then I'll be able to use the other end. I'm going to touch it, not right now, but we'll remove the the 3.3 volts, and then we'll touch it to that same end we just removed the 3.3 volt wire from. We'll touch that, and we'll watch. We'll be able to see using the iLab software the voltage being discharged, or the voltage discharging out of the capacitor. Okay, so my software is open up here. Let's make sure my device is on. I'll plug that in. I wasn't sure if it turned off before it charged up the capacitor. So give that a few seconds to charge, and then we'll open up our Analog 7 software. Okay, and so this will allow us to see, measure the voltage as it changes as the capacitor discharges. Okay, so I'll go ahead and unplug the 3.3 volt port, and then when I touch this end, I'm going to touch and hold it to the resistor. Okay, so I'll start recording. Then I'll hold it, and you can see it discharging there, and then it goes all the way down to 0. Okay, and if you keep it recording and you plug your power source back in, you'll watch and you'll see the capacitor charging back up. Okay, so we saw it initially here, it discharged, and then when I connected the power back up to it, we saw the capacitor charging back up again. Okay, and so what can you say then about how it discharges? Okay, is it, zoom into one of them there? Obviously, it doesn't discharge linearly, right? How does it discharge? And how does it charge? It's definitely not a linear pattern, right? Okay, so then let's actually collect some data now here. And to do this, we'll already charging back up here, so we should be charged. So I'm going to click reset once to start with a fresh graph. And then I'm going to click record, and then I'm going to touch and hold to the resistor. I'll unplug the power first. I'll touch and hold the resistor and watch it fully discharge, and then I'll click stop. Okay, and so what we can see here now, if I use the data cursor, right, I can see what my initial voltage was, right, that flat line up there. Okay, and it should be pretty close to 3.3 volts, right, because that's what the 3.3 volt port puts out on the device. Okay, so you want to record that in your lab report document. And then we're going to take this data, we could actually export it. And so if you look underneath the graph, there's this little kind of square with an arrow, and if you hover over it, it says toolbar. So click on that and go all the way over to the right where it says export to CSV. Okay, and you click on that, and you'll notice a green thing pops up telling you where it's still saved the file to. Okay, and so you could see there, it saves it to your documents folder, to a folder labeled iLab work files. Okay, so this file was created in your documents folder when you installed the software. So I'll go to my Finder window, my documents, I'll see iLab work files, and then there's this folder called export. Okay, and there you'll see there's my my data. Okay, and so you can open this and work with this in any spreadsheet that you want. And so I'm going to open it with Excel, and I'm going to work with it in Excel because that's how what I'm most comfortable with. And you all have access to free Microsoft Office as a student. And so if you don't have that and you want to use it, there's a link in the lab report or the lab instructions. There's a link here where you can go and download it from the IT website if you don't have that and you want to use this. And so the only information that we're going to care about that's been collected is the time in row D, and then row F is the voltage. And for some reason it labels it Cal 0. So I'm going to delete rows A through C, and then this raw column, delete those, right? And then I want to select just a certain amount of this data. So what I want is I want to see the data between when it started discharging and down toward the end of its discharge. So if I put the cursor right about when it starts discharging, well, for me it's pretty close to exactly 1 second. So what I'm going to do, that means before that 1 second, that's when it was just the time period between when I press record and actually started discharging the capacitor. So I don't care about that time. I don't want to analyze that time. So I'm going to follow in the time here. I'm going to go down to 1 second, and I'm going to delete everything before that 1 second. Okay. And I'm just doing this because when I'm going to analyze this in the software, it's going to make it a lot easier for us to see the pattern. Okay, and then as we see, as we go down here, as time goes up, our voltage decreases and it gradually goes down to 0. And I'm going to delete everything after about 0.1, after it discharges to about 0.1 volts. Okay, and that's what I suggest you do, because I think that will give you the best. That'll give you the best data that you can use to model what type of pattern you're seeing here in the graphs. Okay, so now that we've got some data here, we're going to use a tool. It's called Plotly chart software. So in step 8 of the lab instructions, you have the link there. So we'll open that. Okay, and then I'm just going to copy and paste the data from my Excel sheet into this Plotly software. Paste. I'll have to do it. There we go. So now all my data is a lot of data points, but it's all in the software now. Okay, and so what I'm going to do now is I'm going to go over here to where it says plus trace. We're going to add a trace, and it's automatically set to a scatter plot. And then we could choose how to plot it. So our x-axis is going to be time, okay, just like what it was in the iLab software. So we see here that corresponds to column A. So I'll choose column A for my x-axis. And then column Y is going to be our voltage, or the y-axis is going to be our voltage. So we'll choose column B, and then we should see that portion of the iLab software where we collected that data. Okay, and then there's this tool on the toolbar on the left here, and where it says Analyze, you can click on that. and then there's, we're going to choose the curve fitting. We'll click plus fit, we'll add a fit. And then it wants us to select a trace. Well, there's only one right now, it's trace 0. And then down here, you could see, you could choose a family function, okay? So there's linear, quadratic, exponential, all kinds of stuff here. And so you want to pick the fit that fits, it fits the discharge best, okay? So I think it's exponential fit. And then it gives us some parameter estimates. And to find out what these are, we're going to click run. Okay, and it gives us some information here. Okay, and you'll also notice once I chose the exponential function, what it did right up here is it showed us the base form of what is what's the base form of an exponential function. Okay, it's a plus b times e to the something power, right, is an exponential function. Okay, and so these parameters a, b, and c correspond to the parts of the equation here. Okay, so now I'm going to share. I'm just going to kind of work this out for you to kind of so you can see what how this relates to the equation that we have for a capacitor discharging. Okay, so our what we were given was the equation for an exponential function is y equals a plus b times e to the cx. Okay, and so they gave us these numbers based on the fit. Okay, in physics, our equation for the discharging of a capacitor is the V, the voltage, or V final, but the voltage at a specific point in time is equal to its initial voltage, e to the minus t over tau. Okay, and so we had we had this graph, this decay, right? So we had our x and y axes, right? We had the y-axis was voltage, x-axis was time. Okay, so for our exponential function, right, it told us that for every y and the corresponding x, right, goes by this pattern. Okay, and so when we write it in physics for a capacitor discharging, it's this is what the voltage will be at this time. Okay, so instead of writing x, right, we have t for time. Okay, but it's basically the same form, right? So so the only other thing we don't know here is tau. Okay, the Greek letter tau, and tau is what we call it a time constant. Okay, and it's equivalent to the resistance of the circuit times the capacitance. Okay, and we were given what tau is in the parameter estimates. Okay, so we said tau is the same as c. Okay, so our tau is minus 1.698. Okay, so that's our tau. We know tau is equal to resistance times capacitance. Okay, so we're looking for the capacitance. you know the resistance, right? You found the true resistance of this resistor in a previous lab. So now you can calculate what is the true capacitance of this capacitor. Okay, and then we'll do one more thing with the data here. Okay, and basically what we can do is we can make a linear fit of this data. Okay, and the way we do this is we can take our equation for the discharging of a capacitor. So if we take that equation, we need to undo the E, right? In order to get out of this format. So what we'll do is, first thing is we can divide both sides by VI. Okay, and then we can take the natural log of both sides. Okay, so if we take the natural log of both sides, okay, that undoes the E, right? And so on the right side, we'll have minus T, just minus T over tau. And the left side, we have this natural log of V final over V initial. Well, there's a logarithmic identity that says the natural log of BF over VI, A over B, whatever it is, okay, is equivalent to the natural log of the numerator minus the natural log of the denominator. Okay. And then if we divide both sides by T, what we have left is natural log of V final minus natural log of V initial over time equals minus 1 over tau. And what's nice about this is that what is this left side here? It's essentially, it's the slope, right, of the natural log of the voltage, right? So V final minus V initial, right? That's our y-axis over time, or x-axis, that's slope, okay? But it's the natural log of the voltage, not just the voltage. So we can go ahead and find that the natural log of the voltage pretty simply, and then we can plot that. So what we'll do is we'll go back to our Excel. Okay, and this is a pretty simple thing to do here. If you haven't done it before, basically what we do is I'm going to type in to a cell over here in another blank column. I'm going to say equal, and then ln, and then you'll see this function ln pops up. We'll click that, and then I'm going to click over here on B, right? Column B1, as B is the voltage. Click on that. I'll click enter, and it gives me the natural log of 3.11626. Okay, and then if I wanted to repeat that pattern for the rest of the rows, usually you can put the plus sign on the bottom left there and double click on the box. For some reason it doesn't work on mine, but I'll just click and drag it all the way down. If I hold it, drag it all the way down, then it'll plot the natural log of all those data points. So I'll take that data, copy it out of there, I'll paste it into my Plotly data. Okay, and then we could do the same thing that we did to make this exponential curve. Okay, so we'll go back up to traces. We'll add a trace now, another one. So we'll call it trace 2. It'll still be a scatter plot. Our x-axis will still be time, so column A. But this time, our y-axis will be column D, the natural log of the voltage. Okay, and that creates the green line here, which is a pretty linear line we can see. And then we can go back down to under analyze, we can do the curve fitting for this. And now we'll have to add a fit. When we select a trace, this will be trace 2. And it's already set to linear, which is what we want. We'll click run. Okay. And then of course we have the form mx plus b, which we know is the equation of a line, y equals mx plus b. And it gives us the m parameter, which is our slope. Okay, for the left side of that equation that we derived. Okay, and you can see it should be pretty similar to the c, right? C parameter. I just clicked over to the trace 0, the exponential trace data. It should be pretty close, right? So I got 1.698 on the exponential, and then 1.627. Okay, so not exact, but pretty close. Okay, and so now you can use this m parameter, theta, the slope, and what we just derived to determine what is the capacitance through capacitance of this capacitor. Okay, so we derived that, and I have it here in step 11, that whole derivation. All right, so you can use that. So remember this, the left side of the equation, that is the slope, the m parameter, and then we have -1 over tau. And you can again find tau is resistance times capacitance, and you could solve for C. Okay, and then in the final part, we're just gonna basically calculate how much charge there is in that capacitor when it was fully charged up. So the capacitance, remember we said is we symbolize it with capital C, and it's how much charge there is stored in the capacitor. Okay, and we can calculate that, determine that as the amount of charge divided by the voltage. Okay, so if we want to know how much charge there is, it's the capacitance times the voltage. Okay, we want to know what is the initial charge of the capacitor. Well, that means we need to know the initial voltage. And we determined that. We actually took it from our software, right? And we recorded it in our lab document. What was that initial voltage? Okay, and now we determine the capacitance. So now we can determine the initial charge that the capacitor had. So that's one way to do it. Then the other way is we can determine it based on the area under the curve of the voltage time graph that we made with the analog 7 sensor, right? So it's essentially, right, what's the area under that curve will help tell us the initial charge. Okay, so the way we do that is that current, right? What is current? Current is the rate at which charge flows, right? Or we could say dq dt. Okay. And dq, right, is I dt. And so we could say then that the initial charge is the integral of the current dt. Okay, and what is current, right? Remember Ohm's law, V equals I over R. Right, so current is actually voltage over resistance. So we can rewrite this as integral V over R dt. Okay. And we know that the R is a constant, so that can come out of the integral. So we can have 1 over R integral V dt. Okay. And this part here, integral V dt, that's the area under the curve of the voltage versus time graph that we made with the analog 7 sensor. Okay, So from that, we can determine the initial charge. We know the resistance, and we can use the area under the curve of that graph. So we can look at that. Okay, so the area under the curve, we're in data mode. We can just click where, we don't want to click over here, that's not part of the area. We just want under the curve where it's decaying, right, where it's discharging. So if we click and drag over that, that's the area under the curve. And then in our data up here, it tells us, it actually does the integral for us. And the A there symbolizes the area, and that will tell you the area under the curve. And then you can find the initial charge. Okay, and that's it for the RC circuits lab.